Vacuum catastrophe, the worst possible event for the universe. The cosmological constant problem or vacuum catastrophe is the disagreement between the observed values of vacuum energy density and the theoretical large value of zero-point energy suggested by quantum field theory. To understand vacuum decay, you need to consider the Higgs field that surrounds our universe. Like the electric field, the Higgs field varies in strength based on its potential. Think of potential as a track of a ball rolling. The higher it is on the track, the greater the force of the ball. Welcome to our channel Space Venture. In today's video, we are going to talk about vacuum catastrophe. One of the largest inconsistencies found in modern physics is the 122 orders of magnitude difference between the vacuum energy density, estimated by the observations at the cosmological scale, and the quantum vacuum energy density at the Planck scale as calculated or predicted by quantum physics. Just to grasp the magnitude of this difference of 122 zeros, we must recall that each position in a number refers to an order of magnitude. For instance, 10 is in one order of magnitude bigger than 1, and 100 is 2 orders of magnitude bigger than 1. As we keep adding zeros, we see an increase called exponential. From this perspective, the size of a proton is of the order of 10 to 15 m, and the diameter of the universe is approximately 1024 m, which is 24 orders of magnitude bigger than the ruler, and hence is 24 plus 15, 39 orders of magnitude larger than the proton. After rotation, the universe is 40 orders of magnitude larger than a proton. Therefore, the difference of 122 degrees is even bigger. To properly address the vacuum catastrophe, we must first understand its origin. The huge discrepancy of 122 orders of magnitude between the vacuum energy density at the quantum scale and the vacuum energy density at the cosmological scale expresses a serious incompatibility between general relativity and quantum theory, quantum field theory equations. This means that we have one kind of physics that explains and predicts the very small scale and another very different theory that explains the very big scale. This is inconsistent because the very big is composed of the very small, therefore, there must be a coherent transition bridging them. To understand this discrepancy and why the generalized holographic model solves it, in the following, we address how general relativity and quantum physics estimate the vacuum energy density at the cosmological and quantum scales respectively. Then, we will compare these estimations to the exact prediction for the vacuum energy density given by the generalized holographic approach. Vacuum energy density determined by general relativity. General relativity is the geometric theory of gravitation published by Albert Einstein in 1915, and it remains the current model of gravitation in modern physics. The core of general relativity is founded on the famous Einstein field equations that describe the curvature of spacetime caused by whatever matter and energy are present. The common analogy is that rubber represents a deformable spacetime. A bowling ball mass placed on it creates a cup-like depression. If a marble is placed near this depression created by the bowling ball, it rolls down the slope towards the bowling ball as if pulled by a force. In addition, if the marble is given a sideways push, it will trace an orbit around the bowling ball, as if a steady pull towards the ball is swinging the marble along a closed path. Any region distant from massive cosmic objects like stars has non-curved spacetime. The rubber sheet is flat. In that case, if one were to probe spacetime in that far region by sending out a ray of light or a test body, both the ray and the body would travel in perfectly straight lines, like a child's marble rolling across the rubber sheet. Newton thought that gravity was a force. Any two masses in the universe would instantaneously attract one another via a mutual force known as gravity, and he found out that the more massive each mass was, the greater the attractive force between them. The distance squared between the masses played a fundamental role as well. The further they were, the lesser the force. Newton discovered the first law of universal gravitation, which he published in Philosophiae Naturalis Principia Mathematica on July 5, 1687, where g is a proportionality constant that was established empirically, called the gravitational constant. Centuries later, Einstein found a deeper truth, that this force called gravity arises from the shape of spacetime. Einstein's field equations, first published by Einstein in 1915, provide a description of gravity as a geometric property of space and time. Analogously to the way that Maxwell's equations relate electromagnetic fields to the distribution of charges and currents, EFE relates the spacetime geometry to the distribution of mass energiantum, and stress in the spacetime. To compute the spacetime curvature at any point in space using general relativity, you need to know the locations, magnitudes, and distributions of all the masses in the universe. And you also need information about To compute the space-time curvature at any point in space using general relativity, you need to know the locations, magnitudes, and distributions of all masses in the universe. And you also need information about how those masses are moving and how they've moved over time, how all other non-mass forms of energy are distributed, how the object you're measuring is moving in a charging gravitational field, and how the spatial curvature is changing over time. Inserting such information into Einstein's field equations, you can compute the curvature of space-time, which is necessary to calculate the expansion rate of the universe and the rotational speed of galaxies, and compare them to astronomical observations. In technical terms, this means that Einstein's field equations are a set of equations, specifically non-linear partial differential equations which can be expressed in a synthesized form as a single equation. The existence of dark energy and dark matter was inferred so that Einstein's field equations could correctly predict the expansion of the universe and the rotation velocity of galaxies. In this view, dark energy is the source of an expanding force in the universe, while dark matter provides an additional gravity source necessary to stabilize galaxies and clusters of galaxies, since there is not enough ordinary mass to keep them together given the accelerated expansion of the universe. This additional gravity would also explain the rotation velocity of galaxies. Before the expansion of the universe was confirmed, it was believed that the universe was static and composed of the standard matter we are all familiar with, known in technical terms as baryonic matter. This matter is composed of atoms, which are composed mainly of protons and electrons. Since protons are where most of the mass is located, the mass of the atoms is the mass of these protons. In the standard model of particle physics, protons and neutrons are classified as baryonic particles. Therefore, all mass should be baryonic, composed of protons, electrons, and neutrons. After cosmological observations confirmed there was an accelerated expansion of the universe, the baryonic matter was not enough to account for the additional gravitational pull that would keep galaxies from tearing apart during an accelerated expansion. Something seemed to be missing, or was EFE wrong, although widely attributed to Edwin Hubble. The notion of the universe expanding at a determined rate was first derived from EFE equations in 1922 by Alexander Friedmann. Friedmann published a set of equations, not known as the Friedmann equations, showing that the universe might expand, and he presented the expansion speed if they were the case. George Lemaitre independently showed through mathematical derivations that the universe might be expanding, and by observing the proportionality between the recessional velocity of distant cosmological objects and their distances from Earth, he suggested an estimated value for the proportionality constant. When Edwin Hubble confirmed the existence of this expansion 2 years later and determined a more accurate value for the expansion rate, this constant was named after him, the Hubble constant, h0. Hubble inferred this expansion by observing the light emitted by galaxies and found that galaxies are moving away from the Earth at speeds proportional to their distance. In other words, the farther the galaxies are from Earth, the faster they're moving away from Earth. The light emitted by galaxies shifts towards the red end of the electromagnetic spectrum when moving farther away from Earth. This light shift to the red end of the spectrum is also referred to as a redshift. So that is all for this video. Hope you enjoyed the video. Do like, share, and hit the bell button for future updates. See you in the next video.